Hello guys, the topic of this lesson here is going to be when do you get the Hofmann product in your elimination reactions? Well, we know the Hofmann product is the less substituted alkene, is less likely to form in most cases because it's less stable. But there are a few exceptions and we'll get into that. We have 4 exceptions that we have to look at. Organic chemistry classes will expect you to know these exceptions. Let's get it. First one, this is when you have conjugation. What is conjugation? If you have gotten into the conjugated pi system chapter, you know what that is. Most likely you haven't. A conjugated system is just when pi electrons can spread out more because the pi bonds are conjugated together. Here we could form one if we put a double bond here. Pi electrons could migrate over and migrate there. We know that's very stable because if pi electrons can just spread out and run all around the place, it's going to be a lot more stable. So what does this look like mechanistically? Well, your NH2 is going to steal a hydrogen. So no hydrogen is going to donate some electrons, that sigma bond, and then bromine's like, goodbye. So what you get as your product, you're going to get a conjugated pi system. So that just looks like this. And I want you to notice why this is more stable, because that's the whole point. You can't just memorize stuff in organic chem, you gotta know why. These pi electrons, by resonance, if you were to draw the resonance structures, you can see that they can bounce over and bounce over, right? They can kind of move all over the place. And just because of that alone, it's more stable, right? Quite simple, hope you guys understand that. Number 2 here, we have when you use a big, fat, bulky base. You've probably heard this a million times. You'll get the Hofmann product when you use a big, fat, bulky base. Let's kind of explain why that is from the molecular side. Okay, well, we know that we have butoxide, sorry, because it has a negative charge. And we have this here. Well, what you'll look at is you'll be like, I think we're going to get this Zaitsev product here because I know an alkene, if it has more substitution on it, then it's more stable. Well, no, that's wrong because we have a big fat bulky base. If this base, we're going to try to come over here and steal a hydrogen from this carbon, this hydrogen here, it's going to have a hard time. Imagine trying to run to the other side of a room, but there's a big fat dude in the way. You can't, you're gonna get knocked right back, right? So it's gonna repel off. It's impossible. It can't really happen to any appreciable amount. So the base, the big fat bulky base, is gonna come over here to this carbon, which only has 3 hydrogens on it. Itty bitty little hydrogens. There's no steric hindrance basically, and it's gonna just steal that hydrogen real quick and push and form a pi bond, and you're gonna get the Hofmann product. Quite simple there. More stable, more likely to form that way. All right, number 3 here, we have when you have no anti-periplanar hydrogens. What does that mean? Well, anti-periplanar just means come 180 degrees from each other in an anti-conformation. Anti just means if the one's coming towards you, the one's going away from you. So anti-periplanar, away from each other, 180 degrees. We have this in the ring here. This kind of shows this quite well. You would think that we would form the Zaitsev product doing this way because this bromine here would go like that, or sorry, a hydrogen here would go like that, donate the pi electrons, kick bromine off. And you get the Zaitsev product, and you think that would be more stable, but it's not, because this is just impossible to happen. If we were to take a hydrogen here, we know it would be in the dash position. What's also in the dash position? Bromine. So let's draw this kind of as like a Harthworth projection. If you're this base, are you gonna wanna go like that? Do you really think that will work? I sure don't think so, because if I'm that base, I'm gonna come up right up to this side of the compound, and I'm gonna just get shot right back by bromine. Bromine's like, nope, not today, bud. Not today, you ain't stealing that hydrogen. But what if we were to put it here? going up. Well, ammonia can just come from the top, be like, my hydrogen, steal it, donate electrons, make a pi bond. That's kind of what's happening here. And the fact that we're locked in a ring, we can't rotate a single bond. If you had a single bond, you could rotate the hydrogen to make it anti-periplanar, but in this case, you can't. So because of that fact, we cannot physically, with any appreciable amount, make a pi bond here. So what's the other way? We make a Hofmann product by stealing a hydrogen here on a wedged position. So this just goes here, donates electrons, bromine's kicked off. And you're going to get this molecule here. That's your product, quite simple. When you have no anti-periplanar hydrogens, to form a Zaitsev's product, you won't get the Zaitsev product, you'll get the Hofmann product, quite simple. The fourth one is a little harder to understand. It's fluorine, using fluorine here, or just a bad leaving group. Normally you'll see professors just say, oh, if it's fluorine, it's bad, but if it's a bad leaving group in general, and you'll know if it is, if it's not stable enough to leave on its own, it's probably not gonna leave. So, you might look here, you'll be like, ooh, there's a hydrogen there, we can make a Zaitsev product. No, but it's not as inherently obvious. So, fluorine being so itty bitty little small, it's not really wanting to leave. It's like, guys, I can't really hold a negative charge. Why? Mommy, I don't want to go. And it just complains about leaving. It doesn't want to leave. So there's going to be a buildup of charge on these beta carbons. But what do we know about carbocations and carboanions? Well, we know carbocations, the more substituted it is, tertiary carbocations are the most stable. But these aren't carbocations, these are carboanions. The rules are reversed for this. Carboanions are more stable when they're less substituted. So what's going on here? Well, this one's more substituted. This is not more stable. This is. So, because of that fact alone, nitrogen will steal a hydrogen from here. Make the double bond, and fluorine, I guess, will leave, I guess. It doesn't want to leave, but when it does, it's going to leave in that regard. It's going to say, okay, well, I'm more stable to form it that way than that way, right? Because this is a less substituted carboanion. So what you get is this product here, not the Zaitsev product. This is the Hofmann product. Hopefully that made sense to you. Hopefully the way I presented things was a little easier to understand, I know. Especially this example here is terribly explained. It's beyond your knowledge to know why a partial negative charge builds up there. I personally don't even know. I just know that it does, right? But just knowing that fact, just committing that to memory, knowing that it builds up the negative charge, knowing carboanions will help you out a lot. Let's just review here a little bit. Conjugated, when you make a conjugated pi system, the electrons can spread out more. So if you happen to make the Hofmann product that way, you're going to make the Hofmann product rather than the Zaitsevs. Using a bulky base, steric hindrance, all about it, right? Too fat to go and steal a hydrogen from a very sterically hindered side. When you have no anti-periplanar hydrogens, if you see no anti-periplanar hydrogens in a single bond, you can rotate the single bond, but if it's in a ring, it's locked, and you can't rotate it out. And here, when you have a really bad leaving group, builds up a negative charge, whichever beta carbon is less substituted, that resulting hydrogen, if there's one there, will leave and not on the more substituted side. I hope you guys found this helpful, and have a good day now. Goodbye.